So yeah, I'm Catherine Nelson. I'm a data scientist at SAP Concur. If you've not come across Concur before, we offer solutions for businesses around travel and expense. You can book your business travel and get reimbursed from it and manage your invoices, amongst other things. And I'm part of the Concur Labs team, the more experimental side of Concur, where we create new ideas and prototypes to improve the experience of a business traveler. And a couple of my teammates are in the audience. Say hi. Our projects range from virtual reality to Alexa skills via Slack and the expense report that writes itself. And one of our main focuses now and in the future is getting more developers within Concur to use machine learning. Over the last year, we've been thinking about data privacy a lot and how we can incorporate that into machine learning systems. And I'd like to share some of our thoughts and learnings with you today. So when your data involves people and you want to make a machine learning model, I believe that you should always be thinking about ethics, interpretability, and privacy. It's important that your machine learning model is fair to all users, that it's interpretable when it needs to be, and it keeps people's data private when it needs to be. So just to make things clear, this talk is about data privacy and not data security. These things are not the same thing. There's a ton of definitions in this space, but for me, privacy is limiting the amount of data that people share, and security is keeping it in the same place, in a safe place. So what kind of data should we worry about keeping private? We should worry about data that is private or sensitive. A couple of definitions. Private data is personally identifiable information, such as name, address, email, social security number, something that you can use to directly identify a person. There's quasi-identifiers, which are pieces of data that can partially identify someone, and if you have enough of them, you can completely re-identify a person. They leave a unique trace. So examples of this would be something like location data or credit card transactions. And also, when users are given forms, they input all kinds of things into them. So if you're looking at a customer feedback form, you might get names in this, phone numbers, all kinds of things. And sensitive data has consequences if other people find out about it. So this could be health-related personal data or proprietary data that has consequences for a business if it leaks out. So on this slide, you'll see the first appearance of Hugo, Concur Labs' machine learning mascot. Hugo is a node in a neural network. We use him to illustrate all our machine learning designs, and he's going to help me explain the topics in this talk. So data privacy is a huge topic these days. There's legislation such as the GDPR, possible upcoming California data privacy law, and maybe even some new federal legislation coming in the future. It's a big topic for customers, as we've seen from many scandals and media articles. We're all agreed that data privacy is important, but when we get down to the details as developers or data scientists, we'd like to find machine learning techniques that let us add privacy, but still let us train accurate models for users. So the first step in this is to move beyond the opt-in and opt-out model for data privacy. You don't have to just collect all of the data that's available or none of the data. It's better to have a dial rather than an on-off switch. There's a lot of options available, and some of these are controlled by the user, and some of these are controlled by the developer or the data scientist. And the data that you use in a machine learning model doesn't have to be everything that's out there. So looking at a super simple model of how data flows through a machine learning system, this is hugely oversimplified for a production machine learning system, but the data starts with a user, data's collected from the user, and then it's stored in some kind of secure central repository, a database or something like that. It's then extracted from that database to train a machine learning model, And then the model makes predictions that are used in an application. And at every step along the way, there are opportunities to increase user privacy. This is incredibly simple, but it lets us figure out where we can add privacy. So the first possibility is to limit the data that we collect in the first place. And this sits in between where the data is collected from the user and when the data is put into that central storage. We have a Concur Labs project to remove personal data from natural language, which is called the Data Washing Machine Project, illustrated here by Hugo again. This removes directly identifying pieces of personal data, such as names, social security numbers, email addresses, phone numbers, and so on. The washing machine has a privacy dial that allows us to dial up or dial down the amount of personal data that's used. So starting at the lowest levels, we have the pieces of information that are directly tied to a single person, so their social security number, their name, their email addresses. And then as we turn up the dial, we lose more information, and the pieces of data that are removed are not so specific to individual users. And this tool is particularly relevant for the type of data that we encounter at Concur. So the type of data that we see is all around business travel and expense. So I might go on a business trip, book my flights and a hotel through Concur. I take a taxi back from the airport, and then I want to send my receipt to Concur and get reimbursed. So one of the ways we can do that is using an add-in that the Concur Labs team has developed for Outlook, where you can send your email to get to Concur's systems directly from Outlook. You'll see this is the type of data on the right-hand side there that ends up in our systems. And when we look at the full email, we see that as well as the information that Concur needs to get your receipt reimbursed, things like the total amount in that receipt and the date, we've got a whole load of names, addresses, zip codes, phone numbers. And if we use the data washing machine, that allows us to identify this personal data, remove it, and replace it with these placeholders, as you'll see on the bottom of this slide. And we wrap this in an API so that we can use it for any product that we like. But what effect does removing all this data have on a machine learning model? Well, I trained the simplest model I could think of on this type of data. So a binary classification model, just using the text features, that predicts whether a receipt is a hotel or a taxi. And then we can use this to experiment and understand the effect of the data washing machine when we train a model. So as we turn up the privacy dial and remove more personally identifying information, the accuracy decreases a really small amount. We can see that at the lowest levels, the accuracy of the model is just under 98%, but then as we turn up the dial setting to 10, then it decreases just a small amount to just over 97%. So this is really easy to fit into a workflow, but it doesn't provide a strong guarantee of privacy. For example, we can still re-identify people from their transaction history and so on. The way we built this is using a different model for each level on the privacy dial. Some of these are named entity recognition models powered by the Spacey package for Python, which I thoroughly recommend for natural language processing, some regular expressions, and some custom machine learning models. And it's all wrapped up in the Flask API. So the data washing machine is really great for unstructured natural language. And for this data set, turning up the privacy dial has a small effect on model accuracy. But the data can still be used to re-identify people. And we don't have a strong guarantee of privacy here. Another way of not collecting the data in the first place and limiting the data that flows from a user to the central storage is federated learning. So this is an excellent option, but it's a bit more complex. So models that are trained on separate clients are combined together into a production model. The raw data never leaves a user's personal device, but it still allows us to train accurate models. The way it works is that the model weights are sent from a central model to the client, and the client then trains that model with the data that's on user's device, and then returns the updated weights to the central server. And all the central weights are then combined together into one model. And this is available as part of the PySyft package for federated learning, which is developed by the Open Mind organization. So federated learning is useful for many different data types. It can be used on structured or unstructured data, and a big advantage of this is that the data doesn't leave the client, but it can impact the performance of a user's device. So training that model imposes a performance load on that person's mobile phone. And again, we don't have any kind of guarantee of privacy here. The next point where we can add privacy is at the point where we extract data from the central storage and then use it to train the model. So we can increase privacy by only using a subset of the data that we've collected in the first place. And we can do this using K-anonymity, which is often just called anonymization. So K-anonymity states that each individual is indistinguishable from K others with respect to their quasi-identifiers. So as I said at the start, quasi-identifiers are pieces of data that can uniquely identify a person if you have enough of them. So in our data, these are things like location or the amount spent. And I'll walk through an example of how we anonymize data. So here's some structured data of the kind that we might get in a data set. So in the raw data, each person has a unique entry in this table. There's no anonymity. And then we can simply remove some of those data points. We remove the name. We remove the day of the month. And then we can also group the data into buckets, which is what we've done with the amounts. And this now achieves K-anonymity with a K of 3, because each individual, so of these 6 entries in the data set, both sets of 3 are exactly the same. So looking at the effect on another simple classification model. This time I built a simple model, again, to distinguish hotel receipts from taxi receipts, but using the structured data on the previous slide. As we increase K, we can see that there's a really large loss of accuracy. So this is a useful technique for aggregate statistics, where we don't need to know about the individuals in the first place, but it's not so great for machine learning because it has such a big impact on accuracy. So this is a really good technique for structured data, but we can still re-identify people using outside information. So joining between an anonymized data set and another one of many publicly available non-anonymized ones can re-identify data. And this is what happened in a very high-profile case of data that was released by Netflix that was then used to re-identify the people in that data set. And the other big disadvantage is there's just too much data loss here for us to be able to train accurate machine learning models. We need a stronger guarantee of privacy than this. So differential privacy may be the answer here, This is something that can fit anywhere within the system. There's options for fitting it in between the user and the storage, between the storage and the model, and between the model and the prediction. It's something that's seen a lot of research attention, but it only became practical relatively recently. So differential privacy is a formalization of the idea that a query should not reveal whether a person is in a data set. So this means that the probability that a query or a transformation gives a certain result is nearly the same on both of these data sets. One of these has the central Hugo, and the other one doesn't. And the idea is that if your personal data doesn't affect the result of something, then you're happy for it to be included in that database. Or to put it another way, this gives you the ability to say, for any possible output of a program or a machine learning algorithm, well, that was just as likely with my data as without. And this is commonly achieved by some kind of randomization to mask an individual's data values. So one of the simplest ways of achieving differential privacy is the concept of randomized response. So if there's a question that has a sensitive answer, such as, did you stay out late last night? Flip a coin. And if the coin comes up heads, answer truthfully. And if it's tails, flip again and answer just according to what the coin flip says. If it comes up heads, then you have to say yes. And if it comes up tails, then you have to say no. And because we know the probabilities of getting each side of the coin, if we ask a lot of people this question, we can back calculate the proportion of people who stayed out late. And this gives people some kind of deniability so that they don't lose privacy. But this particular way of achieving differential privacy is not so great for machine learning because we only get the overall statistic. A similar example is used by Apple to count the number of emojis that people use. So some of these emojis are randomly swapped when the counts that are returned to Apple are collected from the users. And if the number of users is large, it's a good way to get aggregate statistics. There's also the possibility to turn federated learning that I discussed earlier into a differentially private solution. So in this situation, privacy is achieved by splitting the training data so that the data is not sent to a central source. And then when the parameters are trained on mobile phones, the differentially private part of it limits the amount of information that each client passes to the central server. And if there's a small number of clients for this, say if there's only 100 clients, then the accuracy of the model only reaches about 75%, the blue line in this model, because each user has a certain privacy budget, and which limits the amount of data that can be passed on before it's not possible to before it would be possible to re-identify that person before their data would affect the results of the model too much. So for 100 people, we only reach 75%. But as the number of clients get large, up to 100,000, the accuracy becomes almost the same for the differentially private and the non-differentially private model, as you'll see on the green line in that slide. One of the most exciting options for differential privacy is something that's becoming more common recently, which is training differentially private models. So in particular, deep learning models can expose rare examples from their training data in their predictions. And this could be a large privacy loss for users. So last month, Google announced the release of TensorFlow privacy, and this offers us the strong mathematical guarantees of differential privacy that stop individual users' data being memorized while still maximizing the model accuracy. And this is a huge step forward because it fits in easily to existing workflows. And this puts the randomization of differential privacy within the algorithm. So the predictions of the model don't reveal data about the users. TensorFlow privacy introduces 2 new hyperparameters, along with the standard ones that are normally present in a TensorFlow model. So the new hyperparameters are gradient clipping and the addition of random noise into the model. Gradient clipping prevents models from overfitting, and the amount of random noise can be controlled. So the trade-off here is that as more noise is added, then more information is lost in the training data. The TensorFlow privacy module also allows us to measure the differential privacy parameters after the training has been carried out. So we can measure epsilon, which is the parameter that measures how likely including or excluding any particular point in the training data is likely to change the probability that we learn any particular set of parameters. Again, trying this out on a simple binary classification model. In this case, I used one which is included in the washing machine, and it tests whether a text string is the first line of an address or not. And we can see that as we decrease the epsilon value, which means the increase of privacy, the accuracy stays high to a certain point, then the accuracy takes the dive off a cliff. But it's hard to interpret this epsilon parameter. It's the strength of the privacy guarantee, and lower epsilon is more private, but it doesn't really tell us anything about our real users. For any particular user, how likely are they to really experience a loss of privacy? It does, however, allow us to compare between different algorithms. So Apple, in their publication on differential privacy, quote epsilon values of between 2 and 8 for many of their products. But some privacy researchers say that any value of epsilon greater than 1 is a loss of privacy. So for this data set, we can see that we can just about get below an epsilon of 1 before we lose accuracy. So this is a quote I really like about differentially private models. There's a chance that they can make your model more general, because when models memorize their training data, they're basically overfitting to a single person. So injecting the noise helps you move your model away from overfitting, and your model gets more general. So both machine learning and differential privacy share the same motivations of describing the population and not the individual. So differential privacy is awesome because it offers us a strong mathematical guarantee of privacy. It has a small effect on accuracy for some models, but right now it's still a little complex to implement. But I think we're going to see a lot of increasing use of this in the future. So to summarize how these options fit into our system, between the user and the central storage, we can clean the data. Between the storage and the model, we can anonymize the data. We can jump directly from the user to the model with federated learning. And we can add differential privacy between the user and the storage in federated learning and in differentially private algorithms. If you'd like to learn more, I've written up a lot of these references on our blog at concurlabs.com. And if you scan this QR code, that'll take you directly to that article. So thank you very much.